to it. All right. So let's wrap it up, and so we can take a long break, okay, until the end of this month. So this is the C-square to dynamic flip-flops. We'll close at 9. All right. So please make sure you come back. So this is a C-square, and the feature of this design is that they use two different latches driven by clock and a clock bar, individually. So this is negative latch, this is positive latch. Okay, C-square. All right, it's nothing new. Just cascade together so that it can prevent. And this is more interesting one. This is TSPC dynamic flip-flops. Two single phase. This pair is one latch. This is another one. Okay, and this one is driven by PMOS-based clock, and this is a MOS. Okay, this is the only single phase. The feature is that it's a beauty. The beauty is that it needs only 12 transistors, and the function has been proved that it works just fine. Okay, as I said, some of the students take advantage of this design in many IC designs. Okay, particularly for those high-speed logic. In fact, tomorrow, one of my Indian students is going to have his defense. And his topic is dynamic logic as well, using ANL that we mentioned in our previous lecture. Okay, this is one. And the register that he used is based on this design. Okay, and the chip measurement works just fine, but the problem, I just met him, I asked the question that which are asked by the journal. The problem is for his design, he used giga-level clocks, but the throughput means the bits generated per second is very low. So how can you call this as a contribution when you use a very high-speed clock, but generate limited number of bits per unit time? All right, and I just told him this is a question I'm going to ask tomorrow in your defense. Okay, you got to tell me why this is a contributive stuff. I'm telling you it's not. According to my viewpoint, you are supposed to use a very slow clock. Then you're going to have a very high throughput, and that is called the contribution. Okay, so just like, for example, I use a car as an example. You use a very high-speed, high-power motor, high-power engine, but the distance that you travel in a given period of time is so short. But this is not good. You will spend a lot of energy and power, but you only travel, just 1 mile. The best of the transportation vehicle is that you use a very limited power, maybe no battery. You rely only on solar power, solar panel. Then you can travel hundreds of miles. That is called the contribution. All right? So these kids, I just talked to him during the break because he's kind of nervous because his oral defense is tomorrow morning. I said at the beginning, I warn you at the beginning of the first day you select this topic because it's not convincing enough. All of you will go to a graduate school, and you will be asked by your professors when you enter the graduate school. And then you either follow whatever he said, to do his project or his research, or you will be asked to deliver a creative idea, and realize it on the silicon or on the system. You got to convince your professors, and in the future, you got to convince your committee members that my research is considered as very contributive because of blah, 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 blah. Okay. In this course, all of you are asked to do the report. Do a report because you just follow whatever I said, follow whatever TA said to realize circuits on silicon. But when you become a graduate student, you are now no longer to do the report. You are going to do a research. Research means that it got to be new, it got to be novel, it got to be contributive. Otherwise, you cannot call this as a research. It'll become a report. Okay? Report is just you just repeat whatever is done. Okay? That is a report. Okay? Okay, this is what I let you know. Okay, and this is another example. Okay, over here, that's when clock is 0. When this is 0, this is on. Okay, this is 0. Okay, this is on. So the sample mode, the data will be inverted over here. Okay, over here, there's 0, and this one is 0. The discharging path is gone. And Y will be pre-charged. So when clock is 0, D will be inverted over here, stay there as X. Y will be pre-charged, okay? And clock is 0, this one will be off. It will be whole mode. Okay, nothing will be changed. Okay, Q will be stay as before, nothing will be changed. But when the clock is reversed to be high, then this one is blocked. Nothing will happen here. The X will be used to drive the Y over here. This is on, and it depends on the status of X. If it is high, will be pulled down. Then you have a 0 over there. So off. So the sample mode means this one. This is a pre-charge mode, means Y over here. This is the whole mode, means that's 1. Okay, 1, 2, 3. We have 3 stages of TSPC dynamic flip-flops. When the clock is 0, this one is off. Y right now is being evaluated, and this one is on. Okay, and the outcome of Y will be duplicated at Q because we have 2 inverters over here. So this is a dynamic flip-flops, okay, in this design. 3 stages, and it works just perfectly, literally. And pulse switch, this is a funny thing that you should learn, okay? Pulse switch means that in order to prevent any noise coupled from the output to the input, we like to take advantage of one thing. Okay, this is called the clock chopper. This is very, very cute. Okay, you gotta learn. It is called the chopper or called the edge detector. Okay, let me show you how it works. Okay, let me draw a figure to tell you how it works. Then you understand why this is important. Okay, so this is called a clock chopper, and this is the NAND gate. Here we go. Then we have a clock. Okay, let's assume over here. And we have a second pass. Okay, now this is funny, all right? So we don't care about the rest. We just focus on this one, that's all. So what's going to happen? Okay, let's assume we have a rising edge. Rising edge. Okay, from 0 to 1. The initial state is 0, right? 0. And then suddenly we have a 1. So this 1 will coming over here because there is no stuff in between. So 1 will be directly transferred over here, right? Okay, the initial state 0, 0, 1, 0, 1. Hold on a second. If this is 0, this is 0. Let's start again. When the clock is 0, the initial state is 0. So this is 0, 0, 1. So this is what we're supposed to have. 0 and 1, the end is 1. The beginning stage is 1, sorry. The beginning stage here is 1. Okay, nothing will happen. Right now, let's do some magic change. Okay, right now this goes to 1. This goes to 1, okay? So this one goes to 1 immediately. Immediately, because it's faster. There's a lot of stones on the road. So there's 1 here and 1 over here. So 1 and 1 is what? 0. So this one will be dropped to 0. Drop to 0, very fast. Because we have a lot of blocks over here, right? So the initial state of 1 will not be changed for a while. So, but this one will be changed immediately, right away. So we have 1 and 1, the inverter drops to 0. Drops to 0. This is exactly what happened over here. What over here. Then, okay, the late signal, 1 will be, this one becomes 1, 0, okay, 1, 0, right? When this becomes 0, because it travels for a while, then it turns 0, 0 and 1, okay, will become 0. Then inverted will become 1, and it comes back. And it comes back, 1. This phenomenon is called the clock chopper. Clock chopper. This is what happened over here. Okay, and this is called clock D, means it is delayed over here. This is 1 and 0, and this is NAND gate, 1 and 1. NAND gate becomes 0 for a short period of time. Okay, and this is called edge, sometime detector. Sometimes it's called an edge detector. It detects what? It detects the edge over here. See? Detect the edge over here. So whenever it sees a rising edge, I drop slow for a short period of time. Okay? And it drops a short period of time, and then we like to use this short period of time to drive this dynamic latch. Okay? Because this one will drop. A little bit, it'll become 1. Then this is low, this is a high, and this one will be on. This pair will be on. Then we have an inverted function. All right? Okay. This is very interesting stuff. We generate the narrow clock pulse so that the latch, the C-square MOS latch, will be functioning in a short period of time. Okay, where should be short period of time? And this is a cool thing. Because what? Because it only turned on a little bit. After we carry out the function, then we stop. This is very power efficient. This is why it is very much welcome in industrial application in real circuits because of the power issue. We like safe power, and we like to make it the power efficient. Because right now the carbon right, CO2 emission is a problem of the greenhouse effect of this planet. Now, is that clear to you? Now, this is a clock chopper, or somebody call it the edge detector. The same thing, or the same thing. Okay. Now, if you do follow me, then we can use this one. Okay. You see, whenever you see a pulse latch, okay, you always see an edge detector. Okay, you see the one over there on the top? It is another type of edge detector. Okay, the D goes with the edge detector, or the so-called clock chopper. So, well, when there's a whole mode, okay, this is on the buffer. There's a loop over here. The big one and small one. So the whole mode and the transparent mode. Okay, same thing. All right, it's quite cool, and this is a good circuit. Okay, a clock bar. This is developed by a guy whose name is Partovi. I think this is a guy from East Europe or from Russia. Okay, well, for those students, you can come up with a brilliant idea which can also be proved on silicon. You can name everything, just like you find a new star in the sky. You got the right to name the sky you find, name the star you find in the sky. Okay, this is Partovi pulse latches. Okay, none of my students ever realized these circuits. Okay, now we are heading into the so-called deep water zone. Okay, deep water zone means that a lot of students got confused about this part. It's about the timing estimation. So I like to make it as easy as possible because we only have like 30 minutes left. I might skip a little bit of these slides, and I only pick up a few things for you to understand about what the timing is. So first thing first, let me explain what these figures mean over here. Okay, so this is D, and a lot of this thing means that the data, okay, could be drifted because data could be high, could be low, and then from time to time they could be switched. It can be switch high, but switch high to low, something like that. And the switching time might be drifted. So the drift in time sometimes is called a jitter. Jitter. Let me use this term so that you won't get confused. Timing signal is just like our life. Okay. A lot of uncertainty, okay? A lot of bad things might happen. A lot of noises, a lot of shit's going on. I'm sorry, use bad words, okay? So let me redraw again. The data could be switched from high to low. In the meantime, you also could switch from low to high. This is why we use this kind of representation for you to understand. And this is a time axis. Okay, time is just like the arrow in our in our life. Okay, it going straight forward to that way. It's kind of weird. Time cannot be reversed so far. And then, but the thing is, it might change a little bit earlier. Okay, it might be changed a little bit later, even though that, okay, it's a periodic signal. I use a different color. Okay, it's a different color. And for those signals, you can use a scope to monitor the switching of these signals. Okay, from the leftmost edge to the rightmost edge over here. And this kind of a drifting, the drifting time is referred as a jitter. Is that clear? Is it a jitter? Okay. It's just like, okay, when you are walking on a street, even though you do your best, I like to make sure every step, okay, I strut, okay, is the same. But in fact, you will be highly affected by the condition you are. Right, 10 minutes ago, you were full. 10 minutes later, you are hungry. So we cannot always rely on that, okay? So the data could be drifted in time. And then let's assume the relativity between the clock, the D versus the clock, is that the clock is perfect. Okay, the pulses of a clock is fixed. So as we said before, you want to sample the clock, sample the data. You got to make sure the data, the D, must be stabilized before the edge you want to use. So this period, the time between it is stabilized to the point where the edge, okay, is going up, it is called the setup time. Okay, so you got to make sure all the D are ready to be sampled, T set up before the rising edge, corresponding edge. Again, the data must be stabilized after T hold after this rising edge, after this edge. This is the definition of T setup time and the hold time, all right? Okay, another term for you to understand is that it's called the TQ. TQ means that after the sampling, okay, till the data, till the Q is stabilized. This is the time that it needed to stabilize the output. It's called the TQ. Clock to Q is called the TQ. Okay, these are three terms you've got to remember. Okay, the rest are not that important, but it's still important, okay, for you to do the timing analysis, because a lot of students get confused about this part. But I like to show you the basic stuff You need to understand. Otherwise, when people ask you, you don't know what the hell they are talking about. Okay, T setup, T hold, and TQ. Okay, 3 parameters. Okay, then this is your circuit design in your final project. You have an adder, for example, or multiplier in between. Then as I said, you gotta have a lot of register. Remember I said on Monday morning, you gotta have an array of flip-flop to synchronize all the operands you want to do the addition. Okay, then you gotta have another array of register to do the output generation. Okay, both of them are driven by the same clock. All right? So this is the thing. So let's assume this is addition. So what the entire addition, okay, how much time you need? Okay, now this is a clock. So for every single cycle, for you to finish an addition or a multiplication, this is the lowest speed, the minimum time you need to carry out a single addition. Okay, this is the TQ you need from the clock to the Q1 over here. This is the time for you to carry the data from here to here. This is the TQ you need, right? Then you need some time to finish your addition. This is so-called the propagation delay. That is done in your homework. So you take a long time to do the addition or multiplication. Then D2 is ready. Then D2 is ready. They must be sampled. So you gotta have enough time to be sampled. This is called a setup time. So the clock, the minimum clock for you to finish your addition design, okay, it's a long time. It's a TQ plus TPD plus T setup. It gotta be longer than this one. If your clock period is shorter than this, the summation of these 3 terms, I guarantee you won't see nothing at the output. It's impossible. So from time to time, a lot of students told me that the addition, their addition adder output is wrong. I told them to do one thing: slow down this clock. Slow down the clock. Make the period a little bit longer. Okay, if your addition is wrong when clock is high, but the addition is correct when clock is low, that means you violate that rule. Okay, when the speed is high. Okay, if you lower your speed, lower your clock, and the output is still wrong, that means the total circuit is screwed up. Okay, you have a wrong circuit. Is that clear? So this inequality is a basic rule for you to carry out your function. Right now in this course, all the students only carry out the middle of the combinational circuit, the adder, shifter register, or the multiplexer, multiplier, this kind of thing. It's all combinational. Okay, but you gotta have flip-flop to help you to synchronize everything in the input and at the output. Okay, and this is the basic rule you have to follow. That's it. This is the basic timing equation that I hope my student can remember. Okay, and then the second figure here is the TQ minima. This is the minima you need. Okay, the fattest speed you can clock to TQ1 over there, and you have a very short high-speed circuit, the TPD minima. Then you have a T-hold over there. Okay, this is the worst case. This is the best case. Okay, in IC design, we only care about the worst case. For the best case, we don't care. Okay, we want to make sure every operation is correct, so we always consider the worst case. This is the best. See, minima TQ, minima propagation delay, and enough time for the whole time. That's it. It's perfect. But the world is not that perfect. We always have a problem of variations, noise, okay, and unstable voltage supply. So we don't count on that. Okay, the one we have to follow is the left one. Okay, you got to make sure that This is the equation you want to follow. Okay, and this is called the constraint. Okay, the flip-flop minimum delay constraint. That is the figure in the right corner. Okay, so this means that it's faster. Okay, it's faster. The whole time must satisfy this equation. The whole time must satisfy the quickest one. TQ minima plus the TPD minima. This is for the whole time. Okay, you have two equations to follow. Exclude any one of them, you will never see the correct answer. Basically, most of error, okay, is either you violate the rule number 1, which is the one on the top, or the rule number 2. Okay, this is the basic thing you need. As for everything else, right now it's irrelevant to you. There's another problem, it's called the clock skew. It's kind of scary because a lot of students always forgot this part. Let me redraw the circuit for you, okay? So this is the input D flip-flop. This is your stuff, okay? This is input D flip-flop. And this is output D flip-flop, okay? And both of them, oh, sorry, forgot. Then you have data coming in, data coming out. Both of them are driven by the single clock. Okay, theoretically speaking, both of them, if everything is perfect, they will see the same clock. But after you do your layout, okay, you're going to find out the pass here is a shorter pass. Okay, the one that you use for the output is a longer pass. It's a long pass. So for the clock here and clock that you see here, they will not be the same. Okay, this is clock 1, this is clock 2. Okay, there is always a time difference. There's always a time difference between these two. When you send a rising edge travel through these two passes, okay, there you are going to see the time difference between these two. This is called a skew. Skew is not a jitter. Skew means that we have the same clock at the beginning, but we see different clock at both ends or multiple ends. Okay? So skew is what we are afraid of. Because if the skew is large, okay, we might have a problem, okay, to synchronize everything. So the skew caused by static mismatches in the clock pass, and the difference is in the clock load. It's constant from cycle to cycle. It can be positive or negative. Negative skew is funny. Okay, I'll see you why it's negative. All right, so skew is a problem. Fine. So how do we solve the problem created by skew? All right, so none of my students ever consider this, but this is real, okay? If the skew is driven by this way, we have a longer pass, which is represented by buffer, then we are going to have a positive skew because that goes this way, okay? Input to the output, that way. So you're going to have a positive skew. And these are the whole equation. You don't have to remember it. You just take a picture, you go home, and you can use it in exam, okay? This is the skew. If the skew happened, you got to follow the whole time must be less than these two minus T skew. This is the only difference that you have to be aware. And the T clock, the overall clock cycle, remember we have three terms, right? 1, 2, 3. The T to Q, the delay T to D, and setup, you got to take away from the T skew. This is for positive skew. So what happens if we have a negative? How do we have a negative skew? When the clock is given to the output first, then go through a long path to the input, then you have a negative skew. Okay, then you have a negative skew. The equation is still the same, but the T skew become negative. Okay, equation is still the same. The clock and the data in the opposite direction. So that's why you have a negative skew. When your clock goes to the output first, then you go to the clock is sent to the input, then you have a negative skew. So the equations are the same, but you gotta be aware. Right now the skew is negative. It's negative. Okay, this is negative clock skew. All right, so we have a few topics left. We're going to go over them very quickly because none of them is critical to our circuit design. So these are the three parameters that we mentioned before. Let me refresh your memory again. Setup time, D to Q. Okay, D to Q. This is a propagation delay and the clock to Q delay. Okay. So these are the parameters. So if you were to use the latch-based systems, but the reason why I say it's not important is that none of our students ever use the latch-based system. Okay, none, zero, zip, zero. All of them, so far, 30 years of the career, everybody used D flip-flop, not the D latch. But I got to bring this to your attention. If you were asked this question in the interview to a company, you might like to know this. Okay, I'll show the figure first. Okay, let me use a figure. It's easier for you to understand. See, now those three boxes on the screen, they are not edge trigger. They are level trigger. So if they are level trigger, that means they see that this is a 5-1. Okay, driven by the first clock, and the middle block is driven by another clock, 5-2, and these two must be non-overlapping. That means their edges will be drifted. They cannot, okay, overlap. If they overlap, it's screwed. Okay, it's screwed. Let's assume they are not overlapped. And then the COB1 is a combinational logic. COB2 is another one. Because you cannot equalize the delay generated by these two. So there is a possibility, the delay generated by the first one will be longer or maybe shorter to the delay generated by the second one. So that is why we can use this feature to borrow time, okay, from the first one to the second one. So this is how the figure is, okay? So everything is the same. You got to satisfy the setup time and hold time for the first stage, and you got to satisfy the setup time and hold time for the second stage. It's the same. The only beauty of this design is that we can borrow time. Okay, borrow time over here. We can borrow time. Okay? What do I mean borrow time? Right now, if your adder is too big or your multiplier is too big, you can cut into half. Cut into half, okay? The first half and the second half. And then we can do the time borrow, okay, to over here, because this is only allowed to be done in a latch-based system. For the edge trigger, it cannot be done. Okay, we can cut into half and do the computation for the first one over here. This is for the second one, and this time we can borrow. Okay, this is only allowed in the latch-based system. But as I said, no one ever used it. And the last one is it's much easier to be understood, is the latch-based. Latch-based means that we use a pulse generated by the edge detector or the clock chopper. So we can do the design. We can latch the data over here and do the calculation in the meter. and we use the second process to sample the data. So this one is much more realistic. Okay, it's a pulse latches, one phase of glacis latches. Okay, this is one that we talk about. Okay, why it is so welcome in the industry? Because it'll save a lot of power. Okay, save a lot of power. Okay, and the pipelining. The last topic of this lecture is about the pipelining. Pipelining, none of my students ever done before. Okay, let me explain what the pipelining is. Okay, these are the original design. For example, some of the students select a very complicated multiplier, and then maybe some of the students are very ambitious and aggressive. They like to have a high speed. Okay, so what we do? Okay, this is original design. Okay, and you have something in the middle, and this is D flip-flop, input to the output, just like the one on the top. And you find out the feature of this design is that we can divide into several stages, and then they can run the operation in parallel. So instead of using, because this is very long delay, and they can be partitionable. If this is the case, for example, the addition or the data conversion, we can do that. Then we can do this kind of thing. We can divide it into this several parts, small parts, and then we add D flip-flop. Okay, send it over here. Send it over here. Okay, this is a very long delay. We chop the delay into 3 stages. For example, this delay is TD, and this will become TD divided by 3. With the price to pay is that we have a delay in the middle. But let's assume the TD, after we chop it, and then the process, the first data coming over here, to be processed, this data 1 is coming over to be processed. Then in the next clock, the data 1 is moved to over here, data 1. Coming over here, then data 2 comes in. All right? In the next cycle, the third cycle, data 1 move to over here, and data 2 move over here. And data 3 comes in. Okay, this is the beauty of the design. In the fourth cycle, data 1 is done. Okay, and this one moves over here. This one moves in. Number 4 comes in. Okay, this is what the pipelining means. You will see a lot of pipelining operation in life. Okay, in a lot of factories, they use a pipelining procedure to speed up. Okay, so these are called the processing element, or a station processing element. Okay. If the original data, if you don't do the pipelining, for example, the delay of no pipelining, okay, every data must go through 3 stages. So the 3 times n will be this way. This is a delay. But if you use the pipelining, okay, what is the delay? The delay will become n plus 2. This is number of stages, n plus 2, n plus 3. I think n plus a constant. Okay, n plus, let me see, 1, 2, n plus 3. Okay, and everyone else will get out there at the same, same clock. So this is